Okay, so in the last class we defined exponential of z and log of z, right? So you saw that this generalization is such that when you put y is equal to 0, the imaginary component 0, you will get the real valued function, right? So one thing that is clear, when we define logarithmic function, so it is a multiple valued function, right? Because of that involvement of the term 2n pi I, right? So that means there are multiple branches. So when n is equal to 0, we get principal branch, right? And apart from that, all other branches. For each n, we have other branches, right? So I have shown you a picture which is known as Riemann surface for log z, right? So today I am going to look at another function which is square root of z, to give you a bit more feeling about complex valued function, because this is also a multiple valued function, square root of z, right? So and then from that we build, in fact, then we can give you a general definition of exponential, I mean the exponent function, right? So z raised to power w for some complex number, okay, w. And then we look at certain singularities of these functions. So these are some elementary functions. So once you have exponential function, then I can define sine function. You know that sine x is equal to e raised to power ix plus e raised to power minus ix divided by 2. If you remember that kind of formula, right? So from exponential function you can build sine function and cosine function, right? So those kind of techniques we are going to use to define sine and cosine. And then even you can define hyperbolic function, sine hyperbolic function, cos hyperbolic function. A lot of trigonometric functions can be defined easily. So I am not going to look at all of them, but few basic, okay? And then we are going to talk about singularities. So what are the singularities? A function f of z is said to be singular at a point z is equal to z naught if it fails to be analytic at that point. Okay, if the function is not analytic at a certain point, that point is known as singularity. It turns out that, obviously, so if the function is say 1 over z minus 1, f of z is equal to 1 over z minus 1, what is the singularity here? Z is equal to 1, because you know it is unbounded at that point, right? And obviously it is not analytic at that point, right? So this function is singular at point z is equal to 1, right? Now interestingly, when we look at logarithmic functions, these multiple valued functions, right? So log z, what do you think will be the singular point? 0. Why? Why is that? Huh? Log 0 has no value, but actually from here also you see that what happens, 0, it turns out that it's a branch point, I told you last time, right? It's a branch point, right? Which is common to all branches. So this is normally a singularity, okay? So origin is a singularity. Log z minus 1, what is the singular point? Z is equal to 1, right? So square root of z, what will be the singular point? So you know that's something you can think. So these singular points are very important. So I will tell you there are about 5-6 different kind of singularities. Although a proper definition of singularities are given in terms of Laurent series expansion, which is two-sided expansion of a function. So you know that Taylor series f of z can be written as n is equal to 0 to infinity, all that nth derivative of evaluated at that point divided by factorial n times z minus a raised to power n, right? That's a one side expansion from 0 to infinity. But if you look at the series from minus infinity to plus infinity, that is known as Laurent series. And this Laurent series actually essentially tells you what kind of singularity is there in the function, okay? We will talk about that later on once, because we have to talk about Taylor series and Laurent series for complex valued functions. But at least now I will give you some basic idea about 5, 6 different kind of singularities that are common. Okay. So let me start. By the way, after this, I hope we should be able to finish this much, and maybe then we are going to start integration. Now, integration is beautiful things. It turns out that when we talk about line integral in a complex value scenario, it is connected to double integral in R square. Okay, so that kind of connection is there, which is known as Green's theorem. I am going to talk about that, right? Okay, so basically, so before actually going further into complex analysis, I am going to talk about some two variable integrals, double integral, triple integral, and so on, right? So you already saw limit, continuity, differentiability of two variable functions. Then we will talk about integration. Okay, single valued integration is straightforward. You saw that, right? Riemann sum or Riemann integration, a to b f of x ds is area under the curve, right? That formal sum. Then we can talk about in a similar manner two integration with double integration or triple integration, 2 times integration, 3 times integration at the same time. Okay, and how, I mean, of course they have some physical significance also. We don't have enough time to go on that, but at least I'll give you some basic idea so that you can understand the Green's theorem. Okay, it turns out that if function is analytic in a domain, and if you integrate along a curve C, which is the boundary of the domain, the value of the function is 0. It's a beautiful result. I'll talk about those things. Okay, so it's a, yeah, so it will take some time before we reach at that point. So let us start. Okay, so we were at logarithmic function. After defining exponential function e raised to power z, right, we talked about logarithmic function. So when we look at this expression e raised to power w is equal to z, for what w? It turns out that log z is this quantity. So basically I can formally give you the idea of, yeah, so this is the Riemann surface, okay, of the log z function. So each branch is a separate thing, and origin is common. This is a way, because plotting a 4-dimensional function is a bit tricky, right, and complex, and there are different versions, ways we can do that. But here this is kind of projection. So basically origin is common to all branches. Okay, so what is branch? A branch of a multiple valued function, MVF, function is any single value. Single valued function, capital F, that is analytic in some domain at each point of z, of which capital F of z is one of the values of, I am writing it because it's important concept, otherwise you could have skipped it. Okay, so a branch of a multiple valued function, so it's a multiple valued function like such as log z, right? A branch of a multiple valued function is any single valued function, capital F, that is analytic in some domain at each point of z, f of z is one of the values of f of z. So small f of z is a multiple valued function, capital F of z is a single valued function, okay, which is analytic. So we are restricting to one branch. Okay. So for example, log of z is equal to log of r plus I times theta, where r is positive and minus pi is less than theta is less than pi. This is a branch of a logarithmic function, okay, known as principal branch. This is principal branch, okay. So remember, this capital L means principal log, okay, and small l means actual log, multiple valued function log z, right? So that is the difference. So basically the idea is very simple. So we are restricted to one branch. There are so many branches, right? So normally log z function is not analytic, because at origin it will fails to be analytic, right? It's a multiple valued function. But if you restrict to one branch, the function is analytic, right, at one branch, okay, except that singular point origin. The origin is common to all branches, okay. That is the thing. Then we call it a branch point. Sorry, a branch cut. Basically, I should define what is a branch cut. So a branch cut is a portion of a line or curve, it could be curve also, that is introduced in order to define a branch, capital F, of a multiple valued function small f of z. Okay, so this is a branch cut. So branch cut is a portion of a line or a curve that is introduced in order to define a branch capital F of a multiple valued function f of z, right? Branch cut, which is kind of separating the branches, right? Now branch point, a point which is common to all branches, is known as branch point, okay. Branch point, a point common to all branch cuts actually of f is called branch point, okay. So for example, in the function log of z, which is multiple valued, z is equal to 0 is a branch point, and normally branch points are singular points, okay, they are singular points. And now you see there are certain observations. Number one, log of z1 z2 is what? Log of z1 plus log of z1 plus log of z2, right? The normal, but for the principal log, this is not true. You can verify these things actually. Okay, why it is true? You can look at it. This is easy exercise I am giving you to look at it, okay. That's all about logarithmic function. Now I can give you the idea of square root of z function, okay. square root of z function. So w is equal to square root of z. Z is equal to x plus iy, right? So essentially, what does that mean? This implies that we are solving this equation, w square is equal to z. For what w? If I square, I should get z, right? Z is fixed, given to us. I want to find for what are the w's for which w square is equal to z. How do we solve this? One very simple thing is that just use polar coordinates. Z is equal to r times e raised to power I theta, right? And try to find where the value of w from that expression, right? That you can always do. If you put x plus iy kind of thing, it will be a bit messy. Of course, you can compute the values, a bit lengthy thing. Polar coordinates are quite easy here. So I have to find w. Suppose z is equal to r times e raised to power I theta, right? This implies that w square is equal to r times e raised to power I theta. Correct? Now this can be written as r times e raised to power I theta, r times e raised to power I theta plus 2n pi I. Do you agree with this? What is the value of e raised to power 2n pi I? Anyone? E raised to power 2n pi I. By Euler's theorem, it is cos 2n pi I, cos 2n pi plus I times sin 2n pi, right? And that value is what? 1. So this e raised to power 2n pi, since e raised to power 2n pi is 1, I can add this, right? Fine. So then w will be what? R raised to power half into e raised to power theta plus 2n pi I divided by 2. Correct? What is small n? N is an integer, right? So you can start with, say, n is equal to 0. What will happen? N is equal to 0. You get one value of w, right? So n is equal to 0 will give you w is equal to r raised to power half e raised to power theta I by 2, right? What happens if you take n is equal to 1? Okay, so I think I am writing. There are two things. When n is equal to 1, w is equal to r raised to power half e raised to power theta. N is 1, 2 pi I divided by 2. So it is e raised to power n pi, right? Correct? What is e raised to power n pi? Sorry, n is 1, right? I am sorry. Yes. E raised to power pi I, right? सही है अभी e raised to power pi I? गड़बड़ है? थीटा बाई 2 होगा, थीटा बाई 2 होगा, थीटा बाई hello, yeah, battery is gone, okay, so मैं वहाँ शायद नहीं आ पाऊँगा, but anyway, so see what is a, हाँ, no, theta by 2 आएगा ना. Two will cancel out. N is 1. Oh yeah, theta है. Right? Correct? अरे देखो ये इसको बोलो ना, वो है क्या, बैटरी है देखो किसी के पास. Okay, so got it? It is clear now. So what is e raised to power pi I? Minus 1, right? Okay, so this is your r raised to power half minus r raised to power half e raised to power I theta by 2, correct? So one value is positive, another value is negative, right? So there are two values, right? If you take further n, what will happen? If you take n is equal to 2, again you get positive value. When you take next one, you get negative value. So basically you are going to get, what is happening actually? That means we are moving around origin, right? एक पूरा साइकिल लेते हैं तो एक ब्रांच आती है, राइट? और दूसरा साइकिल लेते हैं दूसरी ब्रांच आती है, राइट? यू ओनली ऑल्टरनेट विद दीज टू ब्रांचेस, एक प्लस एक माइनस वैल्यू दे रही है, राइट? ओके, सो देर आर टू ब्रांचेस of this function. So you can see that picture is really nice. This is the Riemann surface. Two branches are given, right? So when you start moving around one branch for one n, that's one branch, right? For next n, another branch, right? And only two branches you will get, no matter how many n's you take, right? So you are just moving around the origin, right? Okay, so this is a two valued function. Okay, two valued function. So there are two branches, and what will be the branch cut? A line which is passing through x-axis will be a branch cut. Okay, and what is the branch point here? Origin is a branch point here. Okay, so this is something about square root of z, right? Similarly, we can talk about other higher things like z ki power 1 by 3. Now you see 3 branches, right? More beautiful picture. If you take bit further, see another beautiful picture. Z is power 1 by 4. 4 branches now, right? Got the idea? All are multiple valued functions, right? Okay, and they have certain number of branches. So actually w is equal to z raised to power 1 by maybe n or something will give you n branches, right? And so origin is common here also. Origin is a singular point. It's a branch point. Okay, got the idea of Riemann surface? This is the Riemann surface. Okay, so now we can define couple of more functions here. Complex exponents in general. So I already talked about basic thing, z raised to power c. If c is a complex number, we can define like this, log of z. By the way, all these logs are natural log. Base is e. Okay, z is not equal to 0, a complex number, and c is also a complex number. Okay, so just take an example, I raised to power minus 2i. What will be the value? These are all real numbers. Such a beauty. How can this be a real number? So let us see. This is exponential times minus 2i log I, right? From this definition. Okay. Now this is nothing but, now what about log I? Log I is what? A multiple valued function. Value will be log 1 plus I times pi by 2 plus 2n pi, right? This is the value of log I. Log 1 is 0 anyway. It's a real thing, right? So what you are left with is I times 2n plus half times pi. N is a integer. So that means I raised to power minus 2i is nothing but, so you can compute, actually I am leaving something for you, 4n plus 1 times pi, which is a real value. ठीक है? So I mean there are many such things. I think ये सब तो तुम लोगों ने किया होगा हाई स्कूल में ना? किया है? कॉम्प्लेक्स नंबर के साथ तो खेला ही होगा, ये तो खाली खेल है. So I remember my days when I was in, when I was in 12th, actually I used to do these things. So probably you also know, right? Anyway, now we can define certain trigonometric functions. So we know that sin x is equal to e raised to power ix minus e raised to power minus ix divided by 2i. And this you can verify using Euler's theorem, right? This is well known fact. इसी definition को लेते हुए I can define sin of z. And similarly we know cos x is what? E raised to power ix plus e raised to power minus ix divided by 2. So we can define the same way. Sin z e raised to power iz minus e raised to power minus e raised to power iz minus e raised to power minus iz. Slowly लिखेंगे तो हो जाएगा. Same definition copy कर दिया. Now we got a definition for sin z function. Similarly, cos z is equal to e raised to power iz plus e raised to power minus iz divided by 2. Exponential functions we already know, right? We have defined, right? So I know what is e raised. So since I know what is e raised to power z, I can define e raised to power iz also. That's not a big deal, right? Also we have hyperbolic functions. You remember sine hyperbolic y is equal to e raised to power y minus e raised to power minus y divided by 2, and cos hyperbolic y. These are the well known formulas. ये तो तुम लोग हाई स्कूल में यूज करते आए हो, जेई में यूज किया होगा, right? So we can define what is sine of iy from here, I times sine of hyperbolic y. This is a verification. You can verify cos of iy is equal to cos of hyperbolic y. These are simple things for you to verify. So I can define sine of hyperbolic z e raised to power z minus e raised to power minus z divided by 2, and cos of hyperbolic z e raised to power z plus e raised to power minus z divided by 2. Right. जो भी टेक्नोमेट्रिक फंक्शंस को हमने डिफाइन किया है, जो प्रॉपर्टी आ रही है आवाज, सो वी कैन यूज दैट टू डिफाइन ऑल अदर फंक्शंस. यस, बहुत प्रॉब्लम है यार, सब कुछ उड़ा जा रहा है. राइट. एनीवे, फैन भी तेज चढ़ा के रखा है. Okay, now let us look at something very interesting. Can we define sine inverse of z? Sine तो define कर दिया. Right. So we know in the real case sine inverse of x is there, right? Sine inverse of x, cos inverse of x. What can we say about sine inverse of z? So as you know, आपको मुसीबत में क्या चीज़ काम में आती है? गणित, राइट. तो बेसिकली अलजबरा में एक बहुत पावरफुल कॉन्सेप्ट है, जो चीज़ मालूम नहीं है उसको x मान लो, अगर बहुत सारी चीज़ें नहीं मालूम है तो x y z मान लो और सेटिंग्स में डाल दो, एंड देन यू नो द वैल्यू. राइट. जो भी सिनारियो है उसमें डाल दो. द सेम थिंग, हमको साइन इनवर्स z की वैल्यू नहीं मालूम है, ठीक है, मान लेते हैं w है. अब इसका मतलब क्या हुआ? दिस इंप्लाइज दैट साइन इज इक्वल टू, सॉरी, दिस इंप्लाइज दैट z इज इक्वल टू साइन w. w कॉम्प्लेक्स नंबर है, राइट. दैट्स ओके. आई वांट टू फाइंड व्हाट इज w. दिस इंप्लाइज दैट z इज इक्वल टू e रेज़्ड टू पावर i w. डेफिनेशन लगा दिया अपॉन 2i. राइट. w निकालना है हमें. दिस इंप्लाइज दैट, सॉल्व कर लिया इसको. Now this is a square root of 1 minus z square. It's a double valued function, right? Remember, square root of z was a two valued function. This is two valued function, right? So this implies that, so once you know this, sine inverse z is nothing but minus I log of iz plus 1 minus z square raised to power half. You get a multiple valued function, MVF, right? So basically थोड़ा सा कॉमन सेंस यूज करके जितने फंक्शंस डिफाइन करना हो डिफाइन कर सकते हैं, राइट. साइन हो गया, कोसाइन हो गया, साइन हाइपरबोलिक हो गया, कॉस हाइपरबोलिक हो गया. व्हाट एल्स इज लेफ्ट? और कोई फंक्शन याद है? एक्सपोनेंट हो गया. दीज आर एलिमेंट्री फंक्शंस वी आर टॉकिंग अबाउट, राइट. एक और ऐसा भी कॉम्प्लेक्स वैल्यूड फंक्शन है जिसके लिए $1 मिलियन का इनाम है. सुनना चाहोगे? I can tell you about that. Elementary function तो नहीं है, but at least I can mention about it, right? और ये मेरा काफ़ी फेवरेट है. So by the way, in one of the question paper, sample paper, you might have seen one question similar to this. It was a beautiful problem that I created and I still love. केवल क्लास में एक या दो ने सॉल्व किया था. So let me define. I call this function zeta of z is equal to summation n is equal to 1 to infinity 1 over n raised to power z. बहुत सिंपल चीज़ है ना, इनफाइनाइट सीरीज. इसका नाम है रीमान zeta function, one of the beautiful function in mathematics, and it has connection with many things in mathematics, by the way. So z क्या है? Z is a complex number, right? Since it is infinite series, you can talk about convergence, when it will be convergent and so on, right? Okay, so you can talk about. So I think convergence आप इसके बारे में I'll leave it. Find out the domain of definition of this function, right? When this is valid. This function is valid when the function is convergent, right? For all those complex numbers for which this is convergent. Okay. Now, तो रीमान साहब ने क्या किया, इस फंक्शन की स्टडी कर रहे थे, and then he found a relationship between zeta function and some shifting of zeta function. So he found a relationship. There are many relationships which are available. By the way, library में इसके ऊपर एक पूरी book है, Riemann zeta function. If you are excited about it and if you want to earn $1 million, you can look at it. Okay. So then he observed, I mean, there was that, if you look at this line, real part of z is equal to half in the complex plane. Real part of z is equal to half means x is equal to half, right? What people are interested in looking at the zeros of this function. ऐसे कौन से complex numbers हैं जिसको हम यहाँ डालें तो वैल्यू जीरो आ जाए इसकी, right? Very simple thing. What are the complex numbers z for which zeta of z is equal to 0? So we are interested in zeros of Riemann zeta function. Zeros, समझ गए ना? Zeros. So if z is a 0, I mean if कोई दूसरा नंबर ले लो, z is equal to z0 is a 0, so it means z0, zeta of z0 should be 0, right? What are the values of complex number for which this function is 0? This is a open problem. And आपके जो कैलकुलस के महारथी G.H. हार्डी साहब ने बेसिकली ये शो किया कि देर आर इन्फाइनेटली मैनी ज़ीरोज़, इन्फाइनेटली मैनी ज़ीरोज़ हैं इसके, बहुत सारे हैं, ठीक है. नाउ पीपल बिलीव दैट all these zeros will lie on this line, and this is a still open problem. You have to show that all the zeros will lie on this line, real part of z is equal to half. लोगों ने कंप्यूटर प्रोग्राम लिख के वेरीफाई किया है, millions of cases it is coming out to be true. कंप्यूटर की ताकत से इतना तो कर ही सकते हैं, right? And but can you prove it? If you prove it, you will get $1 million. कुछ मेरे को भी दे देना भाई. और what else? Instant fame in the world, right? Many top mathematicians in the world, they tried to prove this result. Even there is one mathematician, Michael Atiyah, I think recently he died actually. So before his death actually he tried to give a proof. Still there are some discussions going on about his proof, but actually many times people want to ask this question कि 100 साल के बाद मान लो आपका पुनर्जन्म होता है तो आप क्या जानना चाहोगे. तो एक मैथमेटिशियन ने जवाब दिया था, मैं ये पूछूंगा रीमान हाइपोथेसिस प्रूफ हो गई क्या. So that is a beautiful thing, right? So maybe you can try. Some of you are very young people and you should actually, very simple question, na? Zero is the find करना है. What are the complex number for which this is 0? Actually what happened, Riemann said that he has found one identity of the Riemann zeta function which is enough to show that all zeros will lie on this line. पर वो जगह कम है थोड़ा, यहाँ पे मैं लिख नहीं पा रहा हूँ, फिर कभी लिखूँगा. तो आज तक तो मिला नहीं वो, ठीक है. उसके बाद उसने लिखा भी नहीं, ठीक है. So this is something interesting, right? Riemann hypothesis. This is known as Riemann hypothesis. $1 million prize. So the book is available. It's a beautiful function, so I told you about it. Okay. I can do some calculation. ये मेरे को अच्छा नहीं लगता है, simple calculations, but I will anyway do one example for you, right? इसमें कुछ मज़ा नहीं है, right? Calculate ही तो करना है. See, sin inverse of minus I की वैल्यू क्या होगी? Minus I times log of 1 plus minus root 2. Okay, and log 1 plus root 2 is equal to log 1 plus root 2 plus 2n pi I. छोड़ो ये मैं तुम कर ही लोगे ना. It's the given there, you know, you can just read. I mean, I don't want to write really simple calculations, right? Just substitute and do it anyway. I think we have some time, so we can talk about singularities. I guess that is more important, okay? Singular point. What is a singular point? Is a point z is equal to z naught. So it is known as singular point if f of z fails to be analytic at z is equal to z naught. So it's a point where the function is not analytic, right? That point is known as singular point. By the way, there is a university also, singular university. देखा है तुमने? नहीं. इसी सब से प्रेरित होकर के लोगों ने नाम रखा है, right? Anyway, first, isolated singularity. There are different types of singularities. Isolated singularity. What is isolated singularity? A point z equal to z naught is known as IS, isolated singularity, if we can find delta positive such that the circle z minus z naught is equal to delta encloses only one singularity z is equal to z naught and no other. So एक सिंगुलरिटी आइसोलेटेड सिंगुलरिटी है. इफ यू ड्रॉ ए सर्किल ऑफ रेडियस डेल्टा, उस सर्किल के अंदर डेल्टा इज ए पॉजिटिव नंबर, स्मॉल पॉजिटिव नंबर, उसके अंदर z नॉट के अलावा कोई और सिंगुलर पॉइंट नहीं है, तो इट इज आइसोलेटेड सिंगुलरिटी, अकेली है, राइट? फाइन, वेरी सिंपल डेफिनेशन. गुड. सेकेंड इज वेरी कॉमन, पोल. व्हाट आर पोल्स? So let us take an example. F of z is equal to 1 over z minus 2 raised to power 4. This function has pole at z is equal to 2. So normally at pole function is unbounded. So this function is unbounded at z is equal to 2. So there is a formal definition. So we say that z is equal to z naught is a pole if what happens? Limit z tends to z naught. Limit limit z tends to z naught. Z minus z naught raised to power n times f of z is a non-zero number. Then we say this is a pole of order n. So this function has pole of order 4, right? Clear, right? Because of this definition, z minus z naught raised to power n times f of z is a non-zero number limit. Okay, it's a non-zero limit. Okay. Let us take another example. F of z is equal to 3z minus 2 divided by z minus 1 whole cube z plus 1 z minus 4. बताइए भाई इसमें क्या क्या है? z is equal to 1 is a pole, right, of order 3. z is equal to minus 1 is a pole of order 1. z is equal to 4 is a pole of order 1. ये सारा डेफिनेशन से निकल आएगा, राइट? एंड z is equal to 2/3 क्या है? z is equal to 2/3 is a zero of this function. वो रिमान जीटा फंक्शन में जैसे जीरो है ना, z की कौन सी वैल्यू डालें कि फंक्शन की वैल्यू जीरो हो जाए? z is equal to 2/3 डालेंगे तो जीरो हो जाएगी, राइट? ओके. So for any function There could be zeros, there could be poles, there could be no pole at all, right? Or there could be, right? That might be a possibility. Okay. I think अभी 3 मिनट है और हमारा काम हो जाएगा. 3 मिनट में we are done. Branch point. So of multiple valued functions are singular points. Okay, if there is a multiple valued function, say log z, so z is equal to 0 is a branch point, it's a singular point. Okay, as I already mentioned. Or z minus 3 raised to power half. So z equal to 3 is a branch point here, right? It's a singular point. Because this is a multiple valued function, right? Similarly, if f of z is equal to log of z square plus z minus 2. So when this value is 0, those will be the branch points. So this z is equal to 1 and z is equal to minus 2. Branch points. Singular points. So I talked about isolated singularity, I talked about poles, and I also talked about branch point. These are the 3 kind of singularities. अभी हमारे पास 3 और हैं, तो 3 मिनट भी हैं, so it will be done. Removable singularity. Okay, I'll give you, take this function f of z is equal to sin z by z. So z is equal to 0 is what? A singular point, right? Because function is unbounded at this point. But we call it as a removable singularity because limit f of z, z tends to 0, exists. Okay, so it's a removable singularity. Got it? Essential singularity. What is essential singularity? A singularity which is not a pole, pole नहीं है, branch point नहीं है, और removable singularity नहीं है, then that singularity is known as essential. Example is f of z is equal to e raised to power 1 over z minus 3. This is not a pole, this is not a branch point, and this is not a removable singularity. So this is known as essential singularity. So z is equal to 3 is a essential singularity. ES, essential singularity. आधे मिनट में बात रखूंगा, ज़्यादा नहीं. So last singularity at infinity, singularity at infinity, right? So basically, if a function is there, and suppose, so basically the type of singularity of f of z at z is equal to infinity is same as if you look at f of 1 over w at w is equal to 0. I mean, they are kind of at infinity. If you want to look at, you can look at origin by just inversing it. Okay, so we can say that f of z is equal to z cube has a pole of order 3 at z is equal to infinity, because that will reverse w is equal to 0, right? I mean, the reverse ho jayega, right? So that's all. सो जितना प्रॉमिस किया था उतना ख़त्म हो गया, राइट. सो वी अब अगले क्लास में, इस हफ्ते कोई क्लास नहीं है, राइट. सो नेक्स्ट क्लास वी आर गोइंग टू स्टार्ट इंटीग्रेशन, कॉम्प्लेक्स इंटीग्रेशन. बहुत जल्दी से कोर्स ख़त्म हो रहा है. आई थिंक अभी हमारे पास 6 लेक्चर है, हम तो बहुत कुछ कवर कर देंगे. ठीक है, तो आपके ऊपर पढ़ाई का लोड थोड़ा ज़्यादा है, बट एज आई मेंशन्ड अर्लियर, आपको केवल सारे सब्जेक्ट्स में केवल 5 घंटे निकालने हैं रोज़. सुबह 4 बजे निकाल लो तो बहुत ही अच्छा है. 4 बजे तो सोने का टाइम होता है तुम्हारा. सो आई वुड सजेस्ट कि 4 बजे उठो, 3 घंटा सुबह पढ़ो, 2 घंटा शाम को ग्रुप डिस्कशन करो, हो गया. लाइफ इज़ ईजी. ओके, टेंशन नहीं लेने का कोई, बिकॉज हमारे कोर्स में लास्ट मिनट तक AA ग्रेड लाने की संभावना रहती है. ओके, सो दैट इज़ देयर. Wish you all good luck. Let us meet tomorrow, next week.